need to really focus on reviewing chapters 10 and 11 before moving further. Okay, so let's look at some announcements here. It's going to be very busy couple of weeks. Today by 11:59 you have to submit phase 1 of the design project. Remember, that has 3 main parts. There's your summary page, which is where you've kind of summarized all the calculations that you've done, and that should probably be filled out by hand and attached at the beginning of your PDF scan of the hand calculations. And so there's those things, and then also the write-up, which describes your assumptions, the research you've done, the data sources, and so on. And remember, from the assignment description, if you happen to have used Excel to double check your calculations, I'd rather not see that. It's required to submit hand calculations for the demand estimation. So that's due tonight by 11:59. Then on Monday, the 24th, so that's after spring break, homework 8 is due. Then Friday of that week is homework 9. And then Monday of the following week is design project phase 2. So just in terms of the scheduling things, anybody have questions related to these announcements? All right. My plan is to be accessible via email or even Microsoft Teams. If you want to get in touch during spring break, then feel free. I'll do my best to be responsive or to pick up if you call on Teams. Just let me know. I have uploaded an Excel file to Blackboard just a few minutes ago. It's in the templates file. Let's see, if we go to our course page here, I put it into Excel files and templates. So specific energy diagram demo file. Please download that. We're going to look at it together just to review one of the examples that we looked at in class on Wednesday. Remember, I showed you how to graph specific energy versus depth. And we looked at this specific case of if we had a 4-meter wide channel and we put 10 cubic meters per second through it. And remember, what we saw would be that there's an infinite, really, number of depths that can give you 10 cubic meters per second through a 4-meter wide channel. And it just, what varies in those different depths is the velocity of the flow. So we looked at the specific case of if the depth is 0.5 meters, and we calculated the specific energy and then found the alternate depth. And so just to refresh your memory on that, the hand calculations on that one, what we did was we had for the y equals 0.5 and for the flow rate of 10 cubic meters per second, we found the specific energy, which is just the amount of energy above the bottom of the channel. We found it was 1.774 meters. And what we see from the figure is that for 1.774 meters, there's another point where we could cross the specific energy diagram, and there's a different depth that has the same amount of specific energy, and that's the alternate depth. That's what alternate depth means, is a place where there's the same amount of specific energy. So we found a cubic equation when we said that we want to find what are the depths associated with this amount of specific energy, with 1.774 meters of specific energy. And so there's one of the 3 roots, which is negative, and we just immediately throw that out because it's not physically meaningful. And then there was the depth that we already had, 0.5 meters, and that happens to be the supercritical depth, where the flow velocity is high. And then there was this unknown root, which we hadn't seen before, and that's the one that we're solving for. This is the other depth that has the same amount of specific energy. And so this shows us numerically how we can set it up and find the alternate depth. And the spreadsheet file I sent you looks like this. Let's just skip straight to the solution tab. So here in the solution tab, I've created the specific energy diagram for 4 meters wide, 10 cubic meters per second. There's just a bunch of different depths. And we don't know when we're first creating a specific energy diagram we don't know exactly which depths we're going to need to put into the specific energy diagram. It's a little bit of an iterative process where you first want to find out what is the specific energy that's associated with these different depths. So the question that was asked in here is, what's the alternate depth? And so if we had a depth of 0.5, so I'll just put that in. You could follow along as well. Put in one of the depths is 0.5, and here we get E equals 1.774. And like, how did we get that? Well, for the given depth, the area is just the width times the depth. The velocity is just Q divided by A. And then E, specific energy, we're using this formula. So it's depth plus Q squared divided by 2GA squared. So here, the E was depth plus, I did this one in terms of velocity squared divided by 2G, since we had the velocities. So here's the amount of specific energy with 0.5. So what we want to do is look down. This is the supercritical. So this is a supercritical depth because the depth is less than the critical depth. The critical depth, remember, is the point of minimum specific energy. It's that leftmost portion, the specific energy diagram. It's associated with what depth gives you the least amount of specific energy. So this is the supercritical depth, and we want to find out what is the alternate depth of that. So we want to find out, which of these depths has the same amount of specific energy. Where are we closest? 1.77. This is pretty close. 1.6. So we want to find out what is the depth that gives us E is 1.774. So we could tinker around with it manually. 1.61. That gets us closer. 1.62. Getting closer. 1.63. Getting tedious. And so instead of that, of course, we're going to do goal seek. So what we'll do is use goal seek to find the Y value that gives us E equals 1.774. Okay, so let's do that now. Data, what if analysis, goal seek. All right, so we want this, our target, to be 1.774 by changing the depth, because we want to give it permission to vary the depth until the resulting specific energy is equal to what we already know for our alternate depth that we're trying to find the other root of. Okay, so it does its thing, 1.58, which, that's the same thing 1.658. So 1.658, that's the same thing that we'd found, solving for the cubic root on the calculator. So I just wanted to demonstrate that, we can do this a number of ways. We can do it graphically, just kind of like lining up the two different crossing points on the specific energy diagram. We can do it numerically by solving for the three roots of a cubic equation, and you do need to do it that way. So I've told you that you need to be able to solve for the unknown flow depth in a trapezoidal channel. Like, you just got to figure that out on your calculator. And another thing, if it's been a while in finding cubic equations, then you definitely need to be able to find cubic equations, because there's going to be a lot of non-uniform flow cases where we're trying to find the depth by solving a cubic equation. So that's one of the ways to do it. And then another is just numerically with goal seek. We can calculate the specific energy associated with a given depth and then optimize the alternate until we find the resulting specific energy. So we did that, and the depth we are looking for is 1.658 meters. That is the alternate of the depth to 0.5 meters. All right. Any questions about this Excel illustration? If not, then I want to give you a hint for the homework. All right. So problem 1125. This is a problem I've been assigning for a long time, and just last year for the first time I finally gave students a little bit of additional assistance in trying to interpret what this problem is actually asking. So we've got a channel that on one side is rectangular and on the other side is trapezoidal. So it's kind of a hybrid. We're not going to be able to use table 10.1 to tell us the wetted perimeter and the area. We have to kind of just use basic geometry to find the area in the wetted perimeter. But with this weird hybrid channel, what they want to find out is what is the shape that is going to give us the minimum cost, and then what's the slope for the flow conditions that are described. So they're telling us that it's got some bottom width B, the water flows at Y, and it's 2-to-1 on the left side, meaning 2 units of horizontal for the side slope for every 1 unit of vertical. So you can see that the area of this is going to be B times Y, and then also adding 1/2 of Y times 2Y. Okay, because a triangle is 1/2 its base times height. Okay, so that's the area. The wetted perimeter will be this length, which is the square root of 2y, the square root of 2y plus y squared. That's how you find the wetted perimeter here. So the wetted perimeter total, though, is this length plus b plus y. So we know that the water flows at 10 cubic meters per second through this channel, and it flows at a velocity of 0.715. So there's a certain cross-sectional area that's implied by that. A equals Q divided by V. So you're going to need to prepare an equation, which I've just told you, to express the area as a function of B and Y. Prepare an equation for the wetted perimeter in terms of Y and B. So we've got two unknowns, and we're trying to find out what's the optimal combination of Y and B in terms of the lowest overall cost. And the cost is due to two factors. It's due to excavation, and it's due to the lining. And so you're going to add together the excavation cost and the lining cost. The excavation cost is related to the cross-sectional area. The lining cost is related to the wetted perimeter. And so you just choose a bunch of different depths, 0.2, 0.4, 0.5, 0.8. Find out if that was the flow depth, how big would B have to be in order to accommodate the flow at that depth. And find out what would be the width for a depth of 0.4. What would be the width at 0.8? Because all of the areas are going to be the same. You know, this is fixed. The area is going to be Q divided by V. So all of them will have the same area. So B is going to be related to whatever Y value you select plus the fixed area. And then for the area that you calculate on each row, then the volume of excavation would be the area multiplied by 1 meter of length into the page. So I think that's all the hints I want to give you. I want to leave a little bit in the unknown here for you to think through it a little bit further, but I suggest that you solve this with a spreadsheet. And I've kind of already illustrated for you what I think the column titles could be in a spreadsheet solution. But the key to this is just that you're going to have two unknowns, but what we're looking for is the overall lowest cost, which is going to be some depth and then the corresponding width that you'd have to have for that depth, and it's going to relate to the least combined excavation and lining cost. And this is actually kind of a real-world type problem. You know, optimization, finding out how you can minimize expenses. And so iteration is sometimes where you have to make a guess. The guess being, what if the flow depth was this or that, and then finding out what are the implications of a certain condition. All right, so any questions about problem 1125? All right. Here's what we're going to do with the bulk of today, is we're going to do some WaterGEMS stuff. And today in our example and in your project, we're going to try and make it so that the pressure never gets above 850 and it never gets below 240. And in the project, your pressures will be low when you have the peak demand. And your pressures will be high at night when nobody's using water inside the city. So you want your system to be designed so that the reservoir is high enough on the hill that it provides adequate pressure inside of the city, but not so high, because if you move the reservoir too high on the hill, then at night the pressure will exceed 850. But you also want to make sure that you can make the pipes as small as possible. So the way to get small pipes is to move the reservoir as high as possible on the hill without going over 850 during the zero flow rate, the static condition. So the design principle is to save money by minimizing the pipe diameter and progressively making the pipe smaller and smaller until you approach a pressure of 240 kilopascals at the peak flow rate. In the project, you can assume that all of the pipes are buried at the same depth underneath the ground. And I've given you a contour map that says the elevation of the ground. So you could, if you want, you could just use the junction elevations to be the elevation at the surface itself, or you could just assume maybe that the pipes are all buried 1 meter below whatever the surface elevation is at those various points. So phase 1 of the project, which you're submitting tonight by 11:59, answers the question, how much water is needed at each of those green arrows on the map? And so what you should be starting to turn your attention to for the next phase of the project is trying to figure out how big the pipe should be, optimizing it, trying to make it as small as possible. And then a secondary consideration is also where to put the reservoir on the hill. So if the pipe's too big, then you'll have plenty of pressure in the network, but it's expensive, unnecessarily costly if you make the pipe oversized. And if the pipes are too small, then you're not achieving the minimum pressure threshold. And the reason why you need a minimum pressure threshold is to ensure that, that there's no backflow into the pipe network, because if the pressure is too low, then contamination can get into the pipe. So it's partly a health and safety issue, but it's also related to providing enough pressure at fire hydrants during an emergency, and also ensuring that people have adequate pressure to do things like shower and consume the water. So 240 is kind of a minimum ordinary operating pressure. So you should really be relentless in trying to downsize the pipes, but satisfying the minimum. All right, this is the network we're going to do in WaterGEMS today. And what's different about this one is we're actually going to put in elevations. You didn't put in elevations last time we used WaterGEMS. Again, we're going to do this one as a schematic. It's not like scaled. We're not drawing on top of an image. You will in the project draw on top of an image. I'll show you after spring break how to do that. So if you haven't already, log into the connection client. Let's see if I'm logged in. Looks like I am. All right, so once you're logged in, then you can start WaterGEMS. Did everybody get a copy of the handout? All right. But you don't have to wait for me. If you already feel like you kind of know the ropes, feel free to start drawing the model. I will narrate through it. Hopefully that's not too distracting, but just a couple of key things. We first of all need to start a new project. So click on this little white paper here, New, if it didn't already start with the model. And then we need to make sure that the units come up as SI. And then we're also going to change the friction loss model over to Darcy-Weisbach. So it's creating the new model. And so down at the bottom right, you can see that it's giving me the coordinates in meters. So it remembered that last time I used the program, I was in SI units. So that's good. But I am going to go into the options here. Options, base calculation options, and instead of Hayes and Williams, I'm going to switch it over to Darcy-Weisbach for maximum accuracy. All right, so I can close that then. So to draw, use this layout button across the home ribbon, layout, and let's just start with this reservoir. So right click to reservoir, dropping a reservoir on the ground, then right click again, change it to junction. So this is A, B, E, F, back up to A again, and escape. All right. Now, I think probably the place to start would be in the junction table. By the way, does anybody need to see a certain thing for drawing the network? Anybody need to see that again? Okay, so go into the flex table for the junction, and we'll rename these junctions. So junction 1, I'm going to call that A. Junction 2 is B. Junction 3, E, and F. All right. Now notice here it says elevation, and I've got a table in the handout that gives us the elevations. It's 0, 9.4, 2.1, and 5.5. That's a ground elevation in meters. So I just want to put that in here. So A is at 0, B is at 9.4, E 2.1, F 5.5. That's going to change the pressure at each of those junctions. If you have a higher elevation, the pressure will be lower, relatively speaking. How do you assign the flow rates? If we look at this network, we've got flow coming out at B, E, and F. Do you remember where to assign the outflows here in this table? Demand collection. Not sure why that's where we do it, but it is. So here, click on demand collection for B, and as soon as we do, we get this little ellipsis, the dot, dot, dot. Click on that and type in the demand of 350 liters per second at B. For junction E, we are going to have an outflow of 450. And junction F, we've got an outflow of 50 liters per second. Okay. So we've got our elevation defined. We've got our flow rates defined. How come it didn't tell us the pressure yet? Well, there's a lot of reasons. For one, we haven't told it where the water is in the reservoir, but mainly it's because we haven't calculated yet. We haven't clicked compute. So before we do that, we have to put in some more information. Let's go into the reservoir properties. So we can either do it as a flex table, reservoir, and type in the elevation, or we just double click on the reservoir itself and it'll bring up a little box over here. It has its properties. So the elevation of the reservoir is 65 meters. That's the physical height of the water in the reservoir. All right. Now, we should put in the pipe characteristics, and what we know is the length and diameter for each of these pipes. So we'll go into the pipe table. So go for the flex table of the pipe. And so pipe 1 is what connects the reservoir to junction A. And the handout says that the diameter of that is 1,000 millimeters, and the length is 10 meters. Now, right now, it thinks that the length I don't even know what it thinks the length is. It doesn't matter because we're going to tell it to use a user-defined length for each of these. So this box over here has user-defined length. Turn that on for all of the pipes because we're going to be defining the lengths of the pipe manually. So reservoir 1 to A, that is a length of 10. Okay, so what this is calling pipe 2 is from A to B. That has a length of 220 and a diameter of 400. Okay, pipe BE is 150 meters long, 350 millimeters diameter. Pipe EF, 80 meters long, 250 millimeters diameter. And then AF is 180 by 300. Now, I don't think the problem statement really tells us what the pipe is made out of. So let's just stick with ductile iron. We'll just stick with that. So we told it the length of the pipe, the diameter of the pipe. The flow rates haven't been calculated yet. But we could. Let's do it. Click on compute. You don't even have to close this box. You can leave it open. And it tells you how much flow is going to be going through each of these pipes. So what we should see is this pipe from the reservoir to A. It should carry all of the flow that we expect to be going out of the system. So if you add up the outflows, there's 450 plus 50 plus 350. So altogether, that's 850. And if you look at our model, it says that there's 850 liters per second going through this pipe into reservoir A. So that's an encouraging sign. We didn't leave any demand collection out. If we want to know the pressure at the junctions, we could open up the flex table for the junctions and we can see here's the pressure at each of the junctions. We're way above our minimum of 240, so we could optimize. But before we do, let's add some annotations. We did that briefly last time. Remember how you do it is over here with this element symbology window. And so let's add the annotations for the pipe and for the junctions. So for the pipe, right-click on the word pipe, new annotation, and let's choose the length. So scroll down here to length, and we'll have it be L equals, and we need to do an offset so it's just not right on top of the pipe. We'll have it do vertical offset 2, meaning it's going to be 2 units. No, X is horizontal. Y is 2. Let's see where that puts it. It's going to put it right on top of those labels, but we'll turn the labels off. So that's fine so far. Let me turn off the pipe label. So we've got the length, and then right-click again on the word pipe. And this time we'll do diameter as our annotation and add this prefix D equals and do the Y offset of -2. Apply. Does anybody have really small text or really small symbols? Sometimes, depending on like how zoomed out or zoomed in you were, you may need to change the size of these. So look at this height multiplier. If I double it, go like 2, then it makes the text larger. So if your text is ever too big or too small, you can adjust it with this height multiplier. You make it really small, make it really big, or just right. Okay, we got the lengths, we got the diameters. Let's annotate the junction pressure. So right-click on the word junction, new, annotation, scroll down to pressure, P equals, and then let's have the offset be 2. Let's just see where that puts it. All right, that seems good. We're going to have to No, that's not good. It's right on top of our labels, and we want to keep the labels. So try to -2. That's better. Okay. And then I guess maybe we should also annotate the flow rate. So pipe, new annotation, scroll down to flow, absolute, Q equals, and then let's do the flow rate at an x offset of 10 and a y offset of 2. Yeah, so we're going to be able to see the length, the flow rate. Everything is good. So we've got it annotated, and we want to optimize now because this pipe network is unnecessarily large. Let's say, just for instance, what if the pipes come in increments of 25 millimeters, meaning that, we can't buy a 399 millimeter pipe, but we could buy a 375. So let's see, if we change this pipe to 375 millimeters, what is it going to do to the pressures everywhere? So, let me just go into the junction table. I'm sorry, the pipe table. Okay, so instead of 400, what if we made it 375? And then recompute. So the pressures are a little bit lower, but still above the limit is 240. So what about maybe making it 300? Go for a more dramatic change. Calculate. Look at the pressures. Up 224. We went below 240. So I was too aggressive in my downsizing. What about maybe 325? Compute. We're looking for this junction here. Is it above 240? Yeah. So is everywhere else. Okay, so now look at the direction of flows. The water goes from A to B, and then from B to E. We had 325 diameter through A to B, but then the pressure is unnecessarily large at junction E, so we could probably next downsize pipe BE. So let's take it from 350, let's see if we could do 325 there. Execute the model. Oh, that hardly even touched the pressure. I think we can go further. Let's try maybe 275. Compute. We still have a long ways to go. We're not even close to the limit. This is a little bit like on Excel, right? The tedious inputting. And what do we usually do in Excel at this point? Goal seek. There is a goal seek for this, but to use it, you have to tell it what is the allowable range of pressures, and then you also have to tell it how expensive pipes are. It's called Darwin Designer. And if you want to use Darwin Designer, you can. I've got a video on YouTube of a former student who explains how to use it. I don't consider that necessary for the project, and honestly, I don't even know if you'd end up saving time. But if you want to, you can use Darwin Designer. It's not so hard to manually iterate and design it. So change it to 250. So the idea is we're progressively going to be changing these pipe diameters until we get just up to the limit of something that's too small. So I think we can go 225. Compute. You get the idea. So it's 1150. We're out of time. I wish we could optimize pipes all day long, but we can't because it's spring break. So the phase 1 is due tonight by 11:59. Next week, no class. I'm sorry, but you've got plenty to keep you busy. So just let me know if you've got any questions or if you need help. Take care.
Dr. White.
Yeah.
Real quick, how did you do the demand collection again?
Demand collection. You go to the junction network, and then you just click on the word like collection off to the side. And so you put the once you do, it gives you this little dot, and you type it in there.
Does it not pop up in the column to the right of it then for demand?
I don't think until you've executed the model. Once you
Okay.
run it, then it'll show.
And if you have water coming